Chapter 19 of Astronomy, The Science of the Heavenly Bodies, by David Todd. Chapter 19, Reflectors, Mirror Telescopes. Cherished with the utmost care in the rooms of the Royal Society of London is a world-famous telescope, a diminutive reflector made by the hands of Sir Isaac Newton. We've already mentioned his connection with the refractor, and how he abandoned that type of telescope in favor of the reflecting mirror, or reflector, in which the obstacles to great size appeared to be purely mechanical. By many, indeed, Newton is regarded as the inventor of the reflector. By the principles of optics, all the rays from a star that strike a concave mirror will be reflected to the geometric focal point, provided a section of that mirror is a parabola. Such a mirror is called a speculum and is an alloy of tin, copper, and bismuth. Its surface takes a very high polish, reflecting, when newly polished, nearly 90% of the light that falls upon it. But the focus where the eyepiece must be used is in front of the mirror, and if the eye were placed there, the observer's head would intercept all, or much, of the light that would otherwise reach the mirror. Gregory, probably the real inventor of the reflector, was the first to dodge this difficulty by perforating the mirror at the center and applying the eyepiece there, at the back of the speculum. But it was necessary to first send the rays to that point by the reflection from a second or smaller mirror in the optical axis of the speculum. This reflects the rays backward down the tube to the eyepiece, or spectroscope, or camera. Another English optician, Cassegrain, improved on this design somewhat by placing the secondary mirror inside the focus of the speculum, or nearer to it, so that the tube is shorter. This form is preferable for many kinds of astronomical work, especially photography. Herschel sought to do away with the secondary reflector entirely and save the loss of light by tilting the speculum slightly so as to throw the image at one side of the tube. But this modification introduces bad definition of the image and has never been much used. A better plan is that of Newton, who placed a small plane speculum at an angle of 45 degrees in the optical axis, where the secondary mirror of the Gregory-Cassegrainian type is placed. The rays are then received by the eyepiece at the side of the upper end of the tube, the observer looking in at right angles to the axis. And a modern improvement, first used by Draper, is a small rectangular prism in place of the little plane speculum, effecting a saving of 5 to 10% of the light. It is not easy to say which type of telescope, the refractor or the reflector, is the more famous, nor which is the better or more useful, or the more likely to lead in the astronomy of the future. When the successors of Dollond had carried the achromatic refractor to the limit enforced by the size of the glass discs they were able to secure, they found these instruments not so great an improvement after all. The single-lens telescopes of great focal length were nearly as good optically, though much more awkward to handle. But the quality of the glass obtainable in that day appeared to set an arbitrary limit to that great amplification of size and power which progress in observational astronomy demanded. Then came the elder Herschel, best known and perhaps the greatest of all astronomers. At Bath, England, music was his profession, especially the organ. But he was dissatisfied with his little Gregorian reflector, and, being a very clever mechanician, he set out to build a reflector for himself. It is said that he cast and polished nearly 200 mirrors in the course of experiments on the most highly reflective type of alloys, and the sort of mechanism that would enable him to give them the highest polish. In his work, he was ably and enthusiastically aided by his sister, Caroline Herschel, most famous of all women astronomers. Upward in size of his mirrors he advanced, till he had a speculum of 2 feet diameter with a tube 20 feet long. 12 to 15 years had elapsed when, in 1781, while testing one of these reflectors on stars in the constellation Gemini, he made the first discovery of a planet since the invention of the telescope, the great planet now known as Uranus. Under the patronage of King George, he advanced to telescopes of still greater size, his largest being no less than 40 feet in length, with a speculum of 4 feet in diameter. 2 new satellites of Saturn were discovered with this giant reflector, which was dismantled by Sir John Herschel with appropriate ceremonies, including the singing of an ode by the Herschel family assembled inside of the tube on New Year's Eve, 1839-40. We have record of but few attempts to improve the size and definition of great reflectors by the continental astronomers during this era. In England and Ireland, however, great progress was made. About 1860, Lassell built a 2-foot reflector with which he discovered 2 new satellites of Uranus and which he subsequently set up in the island of Malta. 10 years later, Thomas Grubb and Son of Dublin constructed a 4-foot reflector, now at the observatory in Melbourne, Australia. Calver, in conjunction with Common of Ealing, London, about 1880-95, built several large reflectors, the largest of 5 feet diameter, now owned by Harvard College Observatory. And rather earlier, Martin of Paris completed a 4-foot reflector. The mirrors of these latter instruments were not made of speculum metal, but of solid glass, which must be very thick, 1/7 their diameter, in order to prevent flexure or bending by their own weight. So sensitive is the optical surface to distortion that unless a complicated series of levers and counterpoises is supplied to support the undersurface of the mirror, the perfection of its optical figure disappears when the telescope is directed to objects at different altitudes in the sky. The upper or outer surface of the glass is the one which receives the optical polish on a heavy coat of silver chemically deposited on the polished glass after its figure has been tested and found satisfactory. But far and away, the most famous reflecting telescope of all is the Leviathan of Lord Rosse, built at Birr Castle, Parsonstown, Ireland, about the middle of the last century. His lordship made many ingenious improvements in grinding the mirror, which was of speculum metal, 6 feet in diameter, and weighed 7 tons. It was ground to a focal length of 54 feet and mounted between heavy walls of masonry, so that the motion of the great tube was restricted to a few degrees on both sides of the meridian. The huge mechanism was very cumbersome in operation, and photography was not available in those days. Nevertheless, Lord Rosse's telescope made the epochal discovery of the spiral nebulae, which no other telescope of that day could have done. In America, the reflector has always kept at least even pace with the refractor. As early as 1830, Mason and Smith, 2 students at Yale College, enthused by Denison Olmsted, built a 12-inch speculum with which they made unsurpassed observations of the nebulae. Dr. Henry Draper, returning from a visit to Lord Rosse, began about 1865 the construction of 2 silver-on-glass reflectors, one of 15 inches diameter, the other of 28 inches, with which he did important work for many years in photography and spectroscopy, and his mirrors are now the property of Harvard College Observatory. Alvin Clark and Sons have, in later years, built a 40-inch mirror for the Lowell Observatory in Arizona, and very recently, a 6-foot silver-on-glass mirror has been set up in the Dominion of Canada Astrophysical Observatory at Victoria, British Columbia, where it is doing excellent work in the hands of Plaskett, its designer. The huge glass disc for the reflector weighs 2 tons, and it must be cast so that there are no internal strains. Otherwise, it is liable to burst in fragments in the process of grinding. It should be free from air bubbles, too, so that the glass is cast in one melting, if possible. This disc was made by the St. Gobain Plate Glass Company, whose works have been ruthlessly destroyed by the enemy during the war. But fortunately, the great disc had been shipped from Antwerp only a week before the declaration of hostilities. Brashear of Allegheny was entrusted with the optical parts, which occupied many months of critical work. The finished mirror is 73 inches in diameter, its focal length is 30 feet, and its thickness 12 inches. A central hole, 10 inches in diameter, makes possible its use as a Gregorian or a Cassegrainian type, as well as Newtonian. The mechanical parts of this great telescope are by Warner and Swasey of Cleveland, after the well-known equatorial mounting of the Melbourne reflector by Grubb of Dublin. Friction of the polar and declination axes is reduced by ball bearings. The 66-foot dome has an opening 15 feet wide and extending 6 feet beyond the zenith. All motions of the telescope, dome shutters, and observing platform are under complete control by electric motors. Spectroscopic binaries form one of the special fields of research with this powerful instrument, and many new binaries have already been detected. The great reflectors, designed and constructed by Ritchie, formerly of Chicago and now of Pasadena, deserve special mention. While connected with the Yerkes Observatory, he constructed a 2-foot reflector for that institution, with which he had exceptional success in photography of the stars and nebulae. Later, he built a 5-foot reflector, now at Carnegie Observatory on Mount Wilson, California, with which the spiral nebulae and many other celestial objects have been especially well photographed. Ritchie's later years have been spent on the construction of an even greater mirror, no less than 100 inches in diameter, which was completed in 1919 and has already yielded photographic results, dealt with farther on, and far surpassing anything previously obtained. Theoretically, this huge mirror, if its surface were perfectly reflective so that it would transmit all the rays falling upon it, would gather 160,000 times as much light as the unaided eye alone. Whether a 72-inch refractor, should it ever be constructed, would surpass the 100-inch reflector as an all-round engine for astronomical research is a question that can only be fully answered by building it and trying the two instruments alongside. Probably 3/4 of all the really great astronomical work in the past has been done by refractors. They are always ready and convenient for use, and the optical surfaces rarely require cleaning and readjustment. With the increase of size, however, the secondary spectrum becomes very bothersome in the great lenses, and the larger they are, the more light is lost by absorption on account of the increasing thickness of the lenses. With the reflector, on the other hand, while there is clearly a greater range of size, the reflective surface retains its high polish only a brief period, so that mere tarnish effectively reduces the aperture, and the great mirror is more or less ineffective in consequence of flexure uncompensated by the lever system that supports the back of the mirror. Both types of telescopes still have their enthusiastic devotees, and the next great reflector would doubtless be a gratifying success. If mounted in some elevated region of the world, like the Andes of northern Chile, where the air is exceptionally steady and the sky very clear a large part of the year. The highest magnifying powers suitable for work with such a telescope could then be employed, and new discoveries added, as well as important work done in extension of lines already begun on the universe of stars. On the authority of Clark, even a 6-foot objective would not necessitate a combined thickness of its glasses in excess of 6 inches. Present discs are vastly superior to the early ones in transparency, and there is reason to expect still greater improvement. The engineering troubles incident to execution of the mechanical side of the scheme need not stand in the way. They never have. Indeed, the astronomer has but just begun to invoke the fertile resources of the modern engineer. Not long before his death, the younger Clark, who had just finished the great lenses of the 40-inch Yerkes telescope, ventured this provision, already in part come true. Quote, "The new astronomy, as well as the old, demands more power. Problems wait for their solution, and theories to be substantiated or disproved. The horizon of science has been greatly broadened within the last few years, but out upon the borderland, I see the glimmer of new lights that await for their interpretation, and the great telescopes of the future must be their interpreters." End quote. Practically all the great telescopes of the world have, in turn, signalized the new accession of power by some significant astronomical discovery. To specify, one of Herschel's reflectors first revealed the planet Uranus, Lord Ross's Leviathan, the spiral nebulae, the 15-inch Cambridge lens, the crepe or dusky ring of Saturn, the 18.5-inch Chicago reflector, the companion of Sirius, the Washington 26-inch telescope, the satellites of Mars, the 30-inch Pulkowa glass, the nebulosities of the Pleiades, and the 36-inch Lick telescope, brought to light a fifth satellite of Jupiter. At the time these discoveries were made, each of these great telescopes was the only instrument then in existence with power enough to have made the discovery possible. So we may advance to still farther accessions of power with the expectation that greater discoveries will continue to gratify our confidence. End of chapter 19.